All right, last time we studied potential energy. We started off by defining, well, reminding you of the definition of single particle energy, and then we combined that into a multi-particle system, and we then defined the energy principle for a multi-particle system. This is all review from your previous physics course here, Physics 172. And we saw that in a multi-particle system, something came up which doesn't come up in a single particle case. Something called the internal energy came up. A single particle has an energy unto itself. It doesn't have a concept like potential energy. Potential energy is an interaction energy. So as soon as I have two particles in the system, I can talk about potential energy. I can talk about the energy due to the interaction of those two particles, and that's what potential energy is. And we saw that if there's any case where the particles inside the system undergo some sort of shape change, a shape change means that the particles in the system are doing work on each other during the change of shape. So in that case, we said, look, internal work is happening. The particles are doing work on each other inside the system, internal to the system. And we'll use that to define something called a potential energy change. So minus the internal work that the particles are doing is equal to the potential energy difference. And potential energy doesn't exist for a single particle. It's an interaction idea. Do you have any questions about last time and how we defined that potential energy change? OK, so today we'll move on and discuss some more about electric potential. I'll also give you an analogy for thinking about electric potential in terms of height, which I find very useful. And we'll relate the potential difference to the electric field. And I'll give you a few different ways to think about it, because these concepts take a while and take some practice to become intuitive. And then we'll also talk about the path independence of potential difference. So let's start with a simple example. So the simple example is the following. Let me have a capacitor. The capacitor we think of as being two parallel plates of charge. And there's a positive sheet charge over here, a negative sheet charge over here. I want to think about a simple case where I can get an electric field that's uniform. And in between those two parallel plates, the electric field is constant. It's uniform. It doesn't change in space. It doesn't change its magnitude, and it doesn't change its direction. So in this example, the electric field is pointing which way? Yep, I see a lot of people doing this. So in this example, the electric field is pointing away from the positive plate towards the negative plate. And if I were to put a proton inside, anywhere inside, it's going to feel that uniform electric field. The electric field we can think of as force per unit charge. It's just sitting there waiting to kick a charged particle should it come inside, right? So it's, as we've said before, the electric field is a real physical object. Right? It's not a figment of physicists' imagination. It's a real thing. And in fact, your eyes can pick up certain ranges of electric fields. So there's a real thing sitting in there waiting to kick that guy. The question we have is as follows. As the proton moves from point A to point B, and these are going to be along the direction of the field, as the proton moves from A to B, what's the change in potential energy of the system? Okay, up here I have everything I'm giving you in the problem, that the system is the charged plates plus the proton. It's going to experience a change in position of 1 centimeter in moving from A to B, 1 centimeter. Delta, when you see a delta of something, delta is change in, and delta is always final minus initial. Delta is final minus initial. So in this case, it's xb minus xa, and that's 1 centimeter. The electric field inside here is 100 newtons per coulomb, and it's uniform and pointing the direction you told me, which is to the right in this example. And the test charge is a proton. So it has charge of 1.6 times 10 to the minus 19 coulombs. So what's the potential energy, change in potential energy of this system during this? Well, we define change in potential energy as the negative of the internal work that the system does on itself. All right? Work, you'll remember, is integral force.dr. And the dr means something needs to be moving. The only thing moving in this system is the proton. Right? If the capacitor were moving too, I'd have to include it in the calculation here for internal work. But we're going to hold the capacitor fixed and just let the proton move. So then the internal work done on the proton is integral f.dr. Okay? And the force that the proton is feeling is QE. This is just directly forces QE. That's the force that guy feels. So that goes right here in this equation for the internal work that's happening. So I have that the change in potential energy is minus integral QE dot dr during this motion. The charge is constant, okay? I need to dot the E into the change in position, right? That gets to be a little bit tricky, is that E dotted into dr, but I set it up so that this is a simpler example where the electric field, like you told me, is pointing to the right, and I'm going to have the motion also be in that direction. So the dot product is just directly the electric field in that direction times the distance I go. So that's that integral. And the electric field is uniform, meaning it's not changing as the proton moves from one spot to another. So Ex can come out of the integral. And then I'm left with integrate dx. And even I can integrate dx in my head. It just turns into the change in x. So altogether, then, the change in potential energy became minus q e delta x in this example, okay? In that example. Do you have any questions about that change in potential energy in this example? Okay? All right. So in a uniform field, the change in potential energy is minus q e delta x. I try to give you a star for the really important equations in the class. So change in potential energy is minus q e delta x in a uniform field. I just want you to calculate for me, given these inputs into the problem, you calculate for me the change in potential energy as this proton moves from point A to point B. Okay? So just calculate change in potential energy here. Okay. Go ahead and tell me now what you're thinking about this problem. How do I figure out which one of these is the right answer? Okay, so he says first, notice that there's centimeters sitting up here. Always convert to SI units first, right? So you convert the centimeters to meters, all right? Okay, and then yep, what do we do next? Oh, okay, so you're going to use process of elimination and rule off B and D because it has to be negative. How do you know it has to be negative?
Because in the equation, the charge has.
Okay, all right, so you just did a real quick. This is awesome. You can always do this on these multiple choice questions. If you can find a way to rule out some answers, that saves you time and also is a good double check on your answer. So she noticed that there's a minus sign here. Everything I'm given in the problem is positive after that, so it must come out to be negative. So I'm going to immediately rule out B and D, and now I just have to choose between A and C. All right, and actually that's, I was watching your answers come in. I get a little bar graph of who answers, and overwhelmingly people were choosing A's and C's. So now we got to choose between A and C. Was there any trickiness here? So how'd you finish the problem? Okay. Okay. All right. So what he said, I'll repeat for the people in the back, is that this is in centimeters. So 1 centimeter is 1/100th of a meter. So when I multiply 1/100th times 100 newtons per coulomb, I got 1. Then it all follows then that it just becomes 1.6 times 10 to the minus 19 coulombs. But then I have to choose the right units. So we're going to choose the negative answer. And then, of course, the rest of the work was to get this 10 to the minus 19 correct. And you just had to do the units conversion from 1 centimeter to 10 to the minus 2 meters. All right. Okay. So there's the answer you just gave me. That the change in potential energy, in this case, is minus 1.6 times 10 to the minus 19 joules. Okay. And in this case, the potential energy, so potential energy change, anytime you see a delta, right? Delta U in this case, delta is always final minus initial, all right? So if the change in potential energy is negative, then did the internal energy increase or decrease in this example? I couldn't hear you. Did the internal energy increase or decrease during the example? Okay, it decreased. And one of the ways that we can think about that is that if I let a system just do what it would naturally want to do, in this case, we moved the proton from A to B. Okay? However, if we had just let the proton go and do what it wanted to do, it would have naturally moved from A to B, right? Because it tends to want to move along, protons move along the electric field direction. So it's doing what it would naturally like to do, which tends to lower its potential energy. So this thing is, this thing being a negative number, the change being negative means the potential energy went down. Does that make kind of intuitive sense, I hope? Okay? We always like to do those double checks to make sure that the intuition is correct. So the electric potential now, what's the electric potential? When we had this test charge, the proton, inside the capacitor, we had potential energy, right? We calculated a change in potential energy, but that means I could also have talked about the potential energy when the proton was just sitting there. Okay, so there is a potential energy just when the proton's sitting there. Now, if I remove the test charge, we know that removing the test charge, well, there's still an electric field there, right? The electric field is due to the plates, and the electric field's a real physical object just waiting to kick the proton if it shows up. But if I don't have the proton there, there's still an electric field present. In the same way, there's something that's waiting to give the system potential energy, right? If the proton should come in, all of a sudden there's potential energy. That means that this capacitor has the ability to give potential energy, okay, when the proton shows up. So electric potential is this idea. It's the potential or the ability, the potentiality, right? The ability to have potential energy should a test charge enter the system. All right. So here's how we define it, though. Electric potential, in this case, all of these are exactly what you saw before. Same exact problem. And the change in potential energy, we said was minus q e delta x in this uniform field case. I'm just going to pull out the test charge, because I want to see, well, if I pull out the test charge, what's left? So there's q. It's the same equation. It's this same equation as up top. I'm just going to pull the q through. The minus sign comes inside, so I have a minus e delta x multiplying the q. And I want to say, well, what's left after the test charge? This part right here, minus e delta x, exists independent of the test charge. Whether I put a test charge in there or not, there's the potential to have a potential energy difference happen. So this part we're going to call then the potential difference, or the potential difference is sometimes called the voltage. Okay, the change in voltage between those two spots. So everything that's left over we'll define as the potential difference, delta V. Do you have any questions so far? Okay, so just a quick note about units. If we define the potential energy change then as Q delta V, what this new thing is, potential, what kind of units must it have? Well, I can work backwards and say, okay, well, delta V is delta V times charge gives me an energy. So V itself must have units of joules per coulomb. If I just work backwards in that equation and divide both sides by Q, I'd get that delta V is delta U over Q, which is energy over charge. So voltage is somehow joules per coulomb. Okay? It's also called volt, named after someone named Volta. So that's what a volt is, joules per coulomb. It also gives us another way to look at the electric field. So far, we've thought about the electric field in terms of something that's permeating space, that's ready to impart a force to a charge should one come along. So we think of the electric field in terms of newtons per coulomb. What force per unit charge would it apply? We have a new way to think about it. We could also think about it in terms of volts per meter. If I look back at this equation again, I see that minus q e delta x is q delta v. Cancel the q's from both sides, and I get that electric field times a distance is voltage. So then that means that electric field must have units of volts per distance. So volts per meter is another way to think about electric field. Do you have any questions about that? Okay, we're going to get a lot more practice thinking about the electric field in terms of volts per meter. All right, now we're ready to define something called an EV. You've used this in a chemistry class, right? Who here has had an EV show up in a chemistry class? Okay, all right, so what's an EV? It comes from this definition. We said that the change in potential energy in this uniform filled case is minus q e delta x, which we then defined as q delta v. An electron volt is another way to describe this energy. So we see that change in potential energy is charge times change in voltage. So an EV, an electron volt, is just the energy required to move one proton through 1 volt of charge. So I take either an electron or a proton and move it through 1 volt of charge. That cost me, as you calculated, it costs 1.6 times 10 to the minus 19 joules of energy. But another way to look at that is 1 electron volt. So an electron volt is the energy to move 1 electron through 1 volt of charge. there's the conversion. 1.6 times 10 to the minus 19 joules is 1 eV of potential energy difference. So the potential energy difference you calculated before was 1 eV. Any questions about that? It's just a definition of units. Okay. All right, good. Time for some Gloucester cheese rolling.
Let's get it going.
Get the cheese!
We have a winner.
That hill is a lot steeper than it looks. That's Gloucester. So if you visit Gloucester, maybe you can also visit their cheese rolling. If you missed the beginning of the video, what little disc shape at the beginning that was cheese. It was a wheel of cheese, and so obviously the idea here is to, well, somehow whoever catches the cheese wins. I'm not sure I get it. Anyway, so why am I showing you this video? Because it cracked me up. No, it's relevant to class. It really is. So we're going to make an analogy today between Gloucester cheese rolling and electrons and protons moving in potential differences, okay? So the analogy is this. The people at the beginning who were running after the cheese, running down the hill, they're like protons. And the hill, the height of the hill, is like a potential. So protons tend to run down a potential hill, just like those people chasing the cheese. And these guys moving up are going to be like electrons. Electrons move the other direction. So here's the analogy. Electric potential is like height. And this is just an analogy, but it helps me get physical intuition about electric field and potential and how charges tend to move. So in the analogy, on the left-hand side, I have what's in this class. On the right-hand side, that's the analogy with heights. So I'll think of potential, okay, voltage. I'll think of potential like a height. So here I've got different heights on that mountain, for example. And I'll think of the positive charge like a ball, or if you prefer, a wheel of cheese. Okay, and so the idea is that in this analogy, I think of potential like height. What does that mean? At every point in space, there is an electric field, right? When an electric field is present, there's a field at every point in space. We said we can think of the electric field like volts per meter. So that means that at every point in space, there's also something called the potential. There's something that relates to the voltage. And I want to map that voltage to a height. So take every point in space, tell me the voltage, and then pretend that's a height. All right? Now, in thinking about that, then the positive charge is going to move in the potential in the same way that a ball would move on a mountain, right? So the ball sitting at the top of the mountain tends to roll down. All right? A positive charge sitting at a high potential tends to want to move to lower potential in the same way that a ball would roll down a hill. The electric field ends up being like the slope of the hill. Okay? So if I think of, well, has anybody been driving in mountains, and as you're driving up the mountain or down the mountain, especially down the mountain, you'll pass a little sign that says steep grade, right? What they mean is that the slope is steep and you should use caution. So the electric field is like that slope, like that sign on the freeway saying you've got a steep grade. That's what the electric field is like. So, and then I also need to think about direction here. I'll get back to that in just a second. Lines of constant potential. So if I want to map out in this analogy, where is the potential the same? That would look just like contours on a map. So has anybody gone hiking and used an actual contour map? Okay. All right. So I'm not a good hiker, but I've been hiking on mountains, and really, I don't think I'll do it again. It was too hard for me. There's a conference that happens in Aspen for physicists. And the thing to do in Aspen, unless it's snowing, the thing to do is to go hiking on mountains. And of course, all my colleagues are 6-foot-tall men, right? And so I say, yeah, of course I'll go hiking with you. And they say to me, well, we're going to go to the top of the mountain. I say, I don't want to go that far. That's too far for me because I'm half your height. So, I told them, look, I'll come along, but I don't want to go the whole way. They said, that's no problem. You don't have to go to the top of the mountain. There's a little turnoff about halfway up. You can hang out at the lake. We'll go to the top. We'll come back and get you. I said, that sounds great. So we're trudging along, and I'm working really hard because they're really tall and they're just moving out, right? And they're used to hiking mountains, and I'm not. And I'm trying not to complain because I'm not a good hiker. I'm trying not to complain. And eventually I ask, where is this turnoff that you were mentioning? And they said, oh, we passed that an hour ago. Oh my gosh. All right, I'm dying. I'm just dying. Trying not to die in front of colleagues, right? That's kind of considered bad. If you go like to the networking stuff, that's how you don't die in front of colleagues. It's bad. I said, how far to the top? And they said 20 minutes. Okay, fine. So anyway, so my experience with this was bad, to say the least. I hope you had a better experience, right? You guys look like you actually enjoyed your hiking. You had a better experience than I did. Good. So when you're hiking, you pay attention to these contour maps, and you know your elevation and that sort of thing. So there's a particular elevation at each point on the mountain, and if you stay at the same elevation and walked around the mountain, that gives you a contour. In the same way, we'll think about constant lines of potential in these electric field situations. Now, thinking again about the mountain, let's pretend we have a mountain range in the room. And see this black line at the front of the classroom? Pretend that's the top of a mountain range. So this is like a ridge, all right? And then on either side, it's going to slope rapidly down, okay? Now, imagine how I define a slope, right? A slope is about a change in height of something, right? You're used to thinking of a slope in terms of, for example, you're used to thinking of slope, well, that slide's not coming for a while. You're used to thinking of slope as something like rise over run, right? So you think about what's the height change versus how far did you move in space. When I'm standing at the top of this ridge, I could think about the slope in that direction, right? If I move in that direction, I'm not going to have a very high slope, right? There's a mountain range going this way. But if I move in this direction, there'll be a high slope, all right? So when I give you this analogy that electric field is like the slope, I have to decide which slope to take, right? Am I going to take the easy slope, or am I going to take the really steep slope? Well, then I go back to the analogy, and I simply say, okay, let's say we put the ball on the top of the mountain range. Which way is the ball going to roll? Yeah, it's going to find the steep path, right? The ball, there's no way that ball is going to roll along the top of the ridge, right? The ball's going to find the steep path. So whatever path your ball takes, walk along that direction and tell me the slope, okay? Tell me what that grade sign would be if you were driving in that direction. That's the electric field. The electric field is like that slope, okay? Do you have any questions so far? All right, we'll get more practice with the analogy, but to me, I find this very helpful for thinking about these problems and for thinking about what would a positive charge do. I simply think about a ball on a mountain range, okay? All right, and the basic idea is here, like the Gloucester cheese rolling, the protons roll down the potential hill. So once I think of potential at every point in space, like a height map, okay, then protons or any positive charges roll down hills. Electrons move the opposite direction, right? So that means it's like electrons roll uphill in this analogy. So the electrons are like these guys at the end running up the hill. And of course, the electric field, like we said, points in the direction that the ball would want to roll, even in a complicated geometry. Sometimes you get a complicated geometry like that. Just think of putting a ball in there. Which way does it want to roll? That's the direction that the electric field points at that point in space. Do you have any questions so far? Okay? And of course, you don't have to think of it in these terms. I'm giving you the analogy that I like to use because I have much more intuition about how a ball rolls down a hill than I do about how a positive charge moves in an electric field, because I can't see the electric field, right? But I have experience with balls rolling down hills. More experience, I guess. Any questions so far? Or complaints? All right. Does the lack of questions mean it's clear? All right, I'm seeing nods. OK, so back to the electric potential then. We can think about it like a height. So we said in this example that we had a change in potential energy. The change in potential energy is minus 1.6 times 10 to the minus 19 joules, or minus 1 eV, right? And so in moving from here to here, from point A to point B, the positive charge went down in potential energy, and there was also a change in electric potential, which we could calculate from that. So we said the change in internal energy is defined as 3 bars, right? 3 bars for the equal sign means defined as, is defined as Q times the potential difference. This defines potential difference. So I can solve for potential difference, delta V. Delta is always final minus initial. So delta V is V final minus V initial, which in this case is VB minus VA. I'm going to go from point A to point B. And then solving this equation for delta V, I find that it's delta U divided by that Q. So delta U divided by Q. And I plug in what we had before. We had that the change in potential energy was minus 1.6 times 10 to the minus 19 joules. I'm dividing by the charge of a proton, which is 1.6 times 10 to the minus 19 coulombs. And altogether, I get a minus 1, right? And it's in volts. Okay, or you can think of it as joules per coulomb, but volts is the more common unit for that. So minus 1 volt. All right, so now you tell me, okay? Use the height analogy if you need to, but you tell me which has the larger potential, point A or point B in this analogy, in this example? A, okay, and why are you saying that A is the larger one? Okay, so you're going back to the math itself, always a good thing to do. So you're going back to the math itself and saying that VB minus VA is a negative number. That means that A, the VA must have been larger. So, all right. And what if I think about the height analogy? How would I translate this? Yeah, go ahead. Yeah, okay, so if I think about what would happen if I just let this proton move on its own, it would naturally tend to move in the direction that it's moving in this example, because it tends to, positive charges follow the electric field direction. And so it must also be rolling down some potential hill. So if it rolls down a potential hill, then its potential went down, right? So good, all right, so VA is larger than VB, and it's just like this guy is rolling down a potential hill. And if you think of the height map in this case, there's a high potential on the left side, low potential on the right side. So it's just like this constant slope, okay, that the proton rolls down. Do you have any questions about that one? Okay, all right. So the positive charges move toward lower potential, just like a ball rolling down a hill. Now, that was the easiest case I can give you, because the electric field was constant, and we had the charge moving parallel to the field. We need to think, though, in a general case where the electric field could be some complicated configuration, and maybe I'll let this charge move in a complicated way. So let me build that up, okay? We already had that in a uniform field with the electric field parallel to x, that the change in potential energy in moving from one spot to another, the change in potential energy was minus E delta x for E parallel to x, okay? Being explicit about the components, I can rewrite this part as change in potential is minus Ex delta x. That's what was happening in our past example, right? The electric field was in the x direction, so E was Ex. All right, so that's this term here. But if I had components in other directions, I need to add them as well. So I should have a term for an electric field pointing in any direction. I should have a term Ey delta y plus a term Ez delta z, okay? If I take a step that's not just along the x direction, maybe I take a step that's partly in the x direction, partly in the y direction, I can add up all those pieces. So Ex delta x plus Ey delta y plus Ez delta z is the total that I need to put in there. And then altogether, I get that change in voltage is minus E dotted into delta x, where delta x is now a vector that simply says I took a step in one direction, that's delta x. The direction I just stepped is the direction of that vector. So if the electric field then, so if it's uniform but pointing in any direction, I generalize to the vector notation. So step one, generalize to vector notation. Now if the electric field is varying in space, what I need to do then is we have to use some calculus. And I'm going to think about an electric field that varies in space, and I have some path I want to take here. Let me, at each spot on the path, think of just taking a little step, just a step delta x. at every step delta x, I'll find out, well, I just stepped in this direction. I'll take the electric field parallel to the direction I'm moving, multiply by the distance I just went. That's 1 bit. Now maybe I'm going to choose a different direction. Now I'll move in this direction. And in that step, I take the electric field parallel to my direction and multiply it by the distance I just moved and add that in. So I can get the delta v all along a complicated path by going, OK, delta v, all right, add up the next delta v, add up the next delta v. Every time I take a step, though, I take the component of the electric field that's parallel to my direction. And as you take the limit, then, that you're going to take your steps smaller and smaller and start taking little bitty baby steps, this turns into an integral, right? That's the magic of calculus. Summing up all those little steps turns into this integral. And so, in general, the change in potential is minus integral from initial to final spot of E dotted into dl. And this is called, excuse me, this is called a line integral, or sometimes you'll hear it called a path integral. It means in order to take this integral dot dl, I need to draw some diagram and take a path from the initial position to the final position. And I'll do that process I just said. All along that path, I'll think of walking along the path, and I'll take a step, I'll add up that contribution, I'll take a step, add up that contribution, and then that gives me the path. Do you have any questions so far about that? Okay, let me tell you that getting an intuition for what this integral means will take you some practice. So practice it, draw out the diagrams, think about, use your imagination and think about yourself walking on that line and taking a step and adding the contribution and taking a step and adding the contribution. That's what that line integral is. Or you could think about it about, I take a step and I scoop up the electric field and put it in my pocket, right? I take a step and I scoop it up and I put it in my pocket, and then I'll just add up everything that came along. All right, and this line integral is very much like stepping along a path. At each step, you use the component of electric field that's parallel to your step direction. Now, this is what I just showed you for potential for potential difference. That change in potential is minus integral from initial to final position of E dot dl. Anytime you see an integral, you can think of differentiating both sides, right? I can take the derivative of that whole equation. So let me think about what that would mean. I want to take a derivative of that whole equation. In this case, electric field is a vector. What I get on the right-hand side is some sort of derivative. That minus sign comes straight down. And inverting this equation to get the electric field out directly would give me minus sign sticks around, and I have dv by dx, where x now is a vector. And that's weird. So let me spend a little bit of time telling you what that means. What's a derivative with respect to a vector? Let's just think first about, let me remind you what a derivative usually looks like, okay? So you're used to thinking, this is just recalling some calculus. I have an axis here of a function plotted out versus some position x. A function is just a line, okay, that goes across that page. And at any particular place, I can think about taking a derivative, df by dx, maybe in this region here, and the way that I know what the derivative is that it has a graphical interpretation. It's the slope of that line at that point, right? And the way I get the slope of that line is I take the rise over run, and then I'll take the limit that box gets really tiny and that the box encloses the point I'm interested in. And then the limit of that rise over run we call the slope, and that is the derivative of that function at that point, okay? So derivative is a slope, all right? But we need somehow a slope that's got a direction. So that's because we're thinking of this case where we've mapped potential at every point in space to height. And so it's like then I have a mountain range I'm on, and I have to decide, am I going to take this derivative in this direction or that direction or that direction? What this math means is it means find the steepest path you can. It means be like the Gloucester cheese. Okay, the Gloucester cheese is not going to run along the top of the ridge. It's going to find the steepest path, right? So this derivative means finds the steepest path and then tell me the slope in that direction, right? Do you have any questions about that physical idea? Okay, sometimes you'll also see this idea represented as what's called the gradient, so minus gradient of the potential. And the gradient is the slope of the hill in the direction the ball wants to roll. Okay, it's in the steepest direction. And of course, when you go back to driving up or down a mountain range, when you're driving down and they give you that sign on the edge of the road that says steep grade, That's what they're calculating. They're saying the gradient is high in that direction, so watch out. Any questions so far about this? Okay. All right. So now I want to think about a consequence of this, which is that taking the potential difference ends up being path independent. So I'll tell you what we mean by that. So I'm going to go back to a simple case and think about the principle, and then we'll generalize to the more complicated cases. So again, let's think about that particle moving a distance to the right in that uniform electric field. Okay? As it does that motion, I can calculate the change in potential. Change in potential in this case was minus Ex times the distance d. Right? So that's the change in potential there. That's how you calculated it before. But I could take a different path from A to B, right? So what if in moving from A to B, I go down first, then to the right, then back up? Okay? Now I could add up all the delta V's along the entire path. So here, I'm going to move down first. This bit here, part 1, the orange line, would then be Ey times delta y. That's what I've written over here, okay? Which is, and the distance I'm moving there in this example is A, so I'd have Ey times A, all right? And then I'd move along this path here, and I'd have Ex minus Ex times d in that example. And then along this direction, I'd have minus Ey times delta y moving back up, okay, which is, again, the distance A. But in this example, which way is the electric field pointing? Yep, the electric field's pointing that way. So what's the magnitude of Ey? Yeah, it's got to be 0, because the electric field's all along the x direction. So these two terms are 0. And when I add up the entire change in potential, I get the exact same answer I did before, even though I took different paths. Okay, so in one place, I went the direct path. And the other one, I took any path I wanted, and I also got the same difference. So the total change in potential is independent of the path taken. Do you have any questions about this particular example? Okay. All right, and now if I think of taking lots of baby steps, I can build up any path I want. So in thinking about the potential difference from some initial point to a final point, and we had this equation already that change in potential is minus integral from initial to final point of E dot dl, where again you need to draw a diagram and tell me the path you're going to take from initial to final point. That's going to equal Vf minus Vi. It turns out that I can take any path I want, right? If I just need to calculate Vf minus Vi, any path I draw in there, I'm going to get the same answer, right? So delta V between 2 points doesn't depend on the path you draw to integrate, which gives you then a hint that, if you have freedom to draw this path, you should probably choose the easiest path you can in order to do your calculation. This is where the height analogy, I think, is really helpful. So if we go back to thinking about the potential difference between here and here as like a height difference, okay? So then I think about, let's put our initial position at the top of a mountain. Here's a nice mountain. Let's all stand at the pinnacle, okay? All right? And then we're going to meet at the bottom of the trail. Here's the trail, and we'll meet at the bottom of the trail, all right? I am going to take the easy route, which to me is going to be the path. So I'm going to walk along the path. It's going to take me a couple extra hours. You guys, if you want, you're just going to roll down the hill like the Chese, okay? Just get down there the fast way, do the little Gloucester Chese. I don't recommend you actually do that, by the way. Am I clear about that? This is just imagination. Okay, but we all meet up at the bottom of the hill. We all had the exact same elevation change, right? Yours was a little faster than mine, but we had the same elevation change. And the same, if I go back then to thinking in terms of potential, if I think of this like a ball rolling down a hill, right, then the potential difference between those points is the same, independent of how you got there, right? Any path down the mountain still gets you down the mountain, and the height difference will be the same, in the same way that the voltage difference between those two doesn't depend which way I calculated the integral. Do you have questions about that? Okay. All right. We're actually done early today. So here's what we did today. Extra time to study, right? You have like 6 extra minutes to study. Quick, get to work. You can do so much physics in 6 minutes.